This is reading week 14. The main physics idea for this week was continuing the idea of electromagnetic radiation from last week, and we had the new concept of the radiating electric field for oscillating charges. And so we can think of this as a charge connected to a spring, and this spring mass system is oscillating, and this thus creates an acceleration. And then, using this acceleration, we can find the acceleration that is in perpendicular to the r vector, which is the location of observation minus the location of the charge. And using that information, we can substitute it into the electric field equation that we got last week to find the E field. And that E field for oscillating charge is going to be 1 over 4 pi epsilon 0 times negative q times the acceleration in perpendicular over c squared times r, and everything is going to be multiplied by sine of omega t plus phi. And this phi is basically a phase shift, and this is due to the oscillating charge that is moving as time progresses, and the oscillating E field created can take some time, which is the phase shift when it reaches the observation location. And similarly, we can use the equation from last week to find the B field magnitude, and that's going to be the magnitude of E field over the speed of light, which is c. And we also looked at the electromagnetic radiation when there is an interaction of radiation with the matter. And as you can see on the right, when there is incident radiation that's coming in certain velocity, it is going to cause the moving charge to have re-radiation, as you can see on the right side. And this re-radiation can be superpositioned with the original incident radiation to find the total sum of the electric field. What I already knew from last week was the idea of radiative E field of a point charge. I learned that charges must accelerate to radiate, and if there is a constant velocity, then there will be no acceleration, thus no radiation. What I did not already know was that you can actually have incident radiation causing re-radiation in a matter, and that it's like an interaction of the matter with the radiation that is resulting in the re-radiation. Something interesting that I learned is that radiative E field from another source can cause another radiative E field, and this is similar to how an induced current in coils can also induce current in other coils, as we learned when we looked at the flux. And how this idea relates to my major in terms of electrical engineering is that electromagnetics, which is EM, is the study of underlying laws that govern the manipulation of electricity and magnetism. And this shows how we use these laws to our advantage. EM is the source of fundamental physics principles behind many branches of electrical engineering, and therefore it indirectly impacts many other branches as well. Something that I thought was interested to look more into was how actually the electromagnetic radiation works, because it was kind of confusing in terms of just looking at the E field of moving charges. And so I thought it would be better to look at how X-rays work. And so based on the NHS website, it says X-rays are a type of radiation that can pass through the body, as you can see on the right. When they pass through, it's just going to penetrate, and they can't be seen by the naked eye, and you can't feel them. And as they pass through the body, the energy from X-rays is absorbed at different rates by different parts of the body. And this is going to cause the radiation to scatter, as you can see on the bottom of the image. And the detector on the other side is going to pick up the X-rays after they've passed through and turn them into an image. and therefore the dense part of your body that X-rays find it more difficult to pass through, such as bone, will show up as clear white areas on the image, and softer parts that X-rays can pass through more easily, such as your heart and lungs, show up as darker areas.